In this session, we discuss nested intervals property theorem. Before going to the theorem, let us understand what are nested intervals. Let us take some examples. We consider a sequence in of intervals defined by in is equal to 0, 1 by n. Closed interval 0, 1 by n. N in n. Now, let us check whether this is a sequence of nested intervals. Let us see the pattern of these intervals. Suppose this is 0 and this is 1 and 2 goes like that. So when n is equal to 1, I1 is actually the closed interval 0, 1. When n is equal to 2, the closed interval I2 is the closed interval 0, 1 by 2. When n is equal to 3, I3 is the closed interval 0, 1 by 3 and so on. Now when you mark these intervals here, the first interval is 0, 1. This is I1. The second interval is 0, 1 by 2. This is 1 by 2. Suppose this is 1 by 3. Then this is I3, 0, 1 by 3. Like that it goes. Here you can see that I1 contains I2, contains I3, contains etc. This type of sequence of intervals we call nested sequence of intervals. Let us take another example. Let Jn equal to minus 1 by n plus 1 by n. Here also we are taking closed interval. We can take open interval also n in n. Let us see what are these type of intervals. When n is equal to 1, I1 is minus 1, 1. Closed interval minus 1, 1. When n is equal to 2, I2 is closed interval minus 1 by 2 minus plus 1 by 2. When n is equal to 3, I3 is equal to minus 1 by 3 plus 1 by 3 and so on. When you mark on this real line, let us see what are these intervals. This is 0, this is minus 1, this is plus 1. The first interval I1 is minus 1, 1. Second interval is minus 1 by 2 plus 1 by 2. Third interval is minus 1 by 3 plus 1 by 3 and it goes like this. Here also you can see that I1 contains I2 contains I3 contains etc. And therefore this is also a nested sequence of intervals, closed intervals. In the place of closed interval, if you take say kn is equal to open interval minus 1 by n, 1 by n, then also the collection sequence kn n in n is a nested sequence of interval. We can see that this k1 contains, k2 contains, etc. Now we define what is a nested sequence of intervals. A sequence in of intervals, whether closed or open, whatever it may be, is said to be a nested sequence of intervals if I1 contains, I2 contains, I3 contains, etc. So this is a nested sequence of intervals. We can see many examples of nested sequence intervals. Now let us study a unique property of this nested sequence of intervals. Now here the question is, suppose in is equal to minus 1 by n 1 by n. The question is whether the intersection n equal to 1 to infinity is equal to empty or not equal to empty. Whether there exists a point in every in, that is, whether there exists at least one point, one number, real number, say x, which belongs to in for all. Let us verify with this in minus 1 by n, 1 by n. See here, this is minus 1, 1, first interval I1, and this is minus 1 by 2 plus 1 by 2, second interval I2. Next is minus 1 by 3 plus 1 by 3, and it goes like that. Now, you can see that the number 0 is always in every in. Therefore, we can assure that intersection n is equal to 1 to infinity is non-empty. In the place of closed interval, suppose we are taking the same minus 1 by n 1 by n, but open interval. Let kn is equal to open interval minus 1 by n 1 by n. Now what happens to the intersection of these intervals? Let us see. So this is 0, this is minus 1 plus 1, the first interval, then minus 1 by 2, 1 by 2 is the I2, second interval, then minus 1 by 3, 1 by 3, plus 1 by 3 is the third interval. It goes like that. It goes like that. Then whether there exists an element x which belongs to every in or not. Now we may believe that this 0 may be in the intersection of minus 1 by n, but when n becomes larger and larger, this minus 1 by n, 1 by n, this length reduced to 0, and this left extreme and the right extreme coincide with 0, and we may think that the 0 is also in minus 1 by n, 1 by n. Suppose there exists an x which belongs to minus 1 by n, 1 by n for all n. Okay. Suppose there is 16x, maybe x0 sometimes. Suppose there is an x which belongs to every minus 1 by n, 1 by n. Now you can see that by here x, let us take x is positive. Let x belongs to minus 1 by n, 1 by n to the right of 0, suppose. You can take any real number, no problem, in between minus 1 by n, 1 by n. Suppose there exists x which belongs to minus 1 by n, 1 by n for every n. Then this is x which belongs to minus 1 by n, 1 by n for every. Now, since x is a real number, by Archimedean property of real numbers, you can find a m, a natural number m in n, such that integer m is greater than 1 by x. 1 by x is possible. If x is taken here a positive, then there exists a natural number you can find which is greater than 1 by x. That which implies x is greater than 1 by m, or 1 by m is less than x. 1 by m is less than x. that is 1 by m is less than x. Now consider the interval minus 1 by m plus 1 by m. That is im, no? Im. Since x is greater than 1 by m, it is very clear that x is not in im. X is not in im, in this im. So what does it show? Which implies x is not in intersection in for every n is equal to 1 to infinity. So there is no x. Actually, it's a contradiction. Thus, we have taken it that all there exists an x which belongs to minus 1 by n, 1 by n for every n. Here we are getting x is not in intersection in n equal to 1 to infinity. Or x is not in, since x is not in in. And therefore, for this example, there is the sequence of nested intervals like minus 1 by n, 1 by n, open intervals. You cannot find a point x which belongs to every I. Now, we will see under what condition this nested intervals has a point in common or there exists points in the intersection of in n equal to 1 to infinity. And this is asserted by the theorem nested intervals property theorem. Intervals property theorem. What is nested intervals property theorem? The nested intervals property theorem states that if sequence in is a sequence of nested closed and bounded intervals. Bounded intervals. Nested and closed and bounded intervals. That is, it is a nested sequence of closed and bounded intervals. Then there exists at least one psi such that the psi belongs to every in for all n. If psi belongs to every in, that is nested intervals property theorem. So the nested intervals property theorem says that if in is a nested sequence of closed and bounded intervals, then there exists a psi which belongs to in for every n. Now we are going to prove the theorem. Let us take the proof of the theorem. It goes like this. Given in is a sequence of closed and bounded interval, nested sequence of closed and bounded interval. So let in, since it is closed and bounded interval, every in you can take as a closed and bounded interval in this one, a and b. That is, every x in in is such that a less than or equal to x less than or equal to b. In is equal to. And I1 contains, I2 contains, etc. So if you take a picture of these intervals, it looks like this. This is I1, A1, B1. And this is A2, B2. Because A2, B2 is contained in I2 is contained in I1. Then A3, B3. Like that it goes. So I1 contains, I2 contains, etc. Where each in is a closed bounded interval A and B. Now consider the set. Consider the set of all left endpoints of these intervals. Left endpoints of these intervals. That is, we are considering the set AK, K in, K in. Clearly, B1 is an upper bound of the set AK, K in. Clearly, B1 is an upper bound of this set. Let this set be S, this set is. Now by supremum axiom, supremum property of real numbers, the set S has a least upper bound. By supremum property of R, S has a upper bound, supreme. Let psi equal to supremum of S. Let psi be supremum of the set S. Then clearly every ak or an is less than or equal to psi for all n. That is very clear. Now we are going to prove that this psi belongs to every a and b. Every a and b. We are going to prove this psi is somewhere here, psi, which belongs to every a and b. Already we got here an is less than or equal to psi. That means psi is the least upper bound of the left extreme points a1, a2, etc. And we will prove every bk's are such that bk is greater than or equal to psi. Every bn is greater than or equal to psi. So that is what we are going to prove. Now consider again the set ak k in n. Here psi is the supreme of this set S. Psi is the supremum of the set S. Now you keep n fixed. Let us keep n some fixed. Take bn, some bn for some fixed n we are taking. Now there are two cases here. This case varying over natural numbers, and this bn is some fixed right extreme for some fixed n, and hence this k either it is less than or equal to n or k greater than or equal to n. If you take any k, it is either less than or equal to n or k greater than or equal to n. Now let k is less than or equal to n. If k is less than or equal to n, the interval ak, bk and an, bn are such that the intervals ak, bk and an, bn are such that, since we know in is a nested sequence, an, bn is a nested sequence of intervals. So since k is less than or equal to n, this ak, bk and an, bn are such that an, bn, the closed interval an, bn is contained in ak, bk. That is the picture. It looks like this. This is ak, bk. This is an, bn. This is an, bn. Now, in this pattern of placement of intervals, clearly ak is less than or equal to an is less than or equal to bn. ak is less than or equal to an is less than or equal to bn. That is, ak is less than or equal to bn. ak is less than or equal to bn. You take it some number 2. Now, let us take the other case, k greater than or equal to n. K greater than or equal to n. In that case, the intervals ak, bk and an, bn are such that the intervals, in this case k greater than or equal to n, the intervals ak, bk and an, bn are such that ak, bk AK, BK is contained in A and B. A and B. So in the picture we can place A and B if these conditions, satisfying this condition, we can place like this. A N B N is like this. If it is, then AK BK is like this. Now in this placement of intervals also we can see that AK is less than or equal to BK, AK is less than or equal to BK, which is less than or equal to BN, which implies there is AK is less than or equal to BN number 3. So in any of these cases, whether K is greater than or equal to N or K less than or equal to N, AK is less than or equal to BN, AK is less than or equal to BN. So whether K is less than or equal to N or K greater than or equal to N, the AK is always less than or equal to B. This is for some fixed N we have taken, AK is less than or equal to B. And AK may be any integer, K varies over natural numbers. That means AK is less than or equal to Bn for all K in N, for all K. And there is Bn is an upper bound of the set S equal to AK K in N, K in N. Bn is an upper bound of the set S. Since psi is the least upper bound of this set, it is very clear that psi is less than or equal to Bn. Psi is less than or equal to Bn number 4. Now you just keep varying N. For some fixed N we have psi is less than or equal to Bn. Now keep varying N. Whatever Bn if you take, psi is always less than or equal to Bn only. That means since N is arbitrary, we have the result that arbitrary psi is less than or equal to Bn for all N. Psi is less than or equal to Bn for all N. There is the result 5. Let it be. This is 5. So earlier we proved An is less than or equal to psi. An is less than or equal to psi for all N. Indication number 1. Here we have got a psi is less than or equal to Bn for all N. Thus, from 1 and 5, we have the result that An is less than or equal to psi, less than or equal to Bn for all N. That is psi which belongs to In for all N, which implies intersection of In, N is equal to 1 to infinity, is non-empty. So this is nested intervals property theorem. So if In is a nested sequence of closed and bounded intervals, then intersection In is non-empty. That is nested intervals property theorem. And the theorem will be violated if any of these conditions. Suppose we take In is a nested sequence of open intervals, then there are cases where intersection In need not be non-empty. Similarly, if In is a nested sequence of unbounded intervals, then also the intersection need not be non-empty. It can be empty also. For that, we can cite examples. For this example, we have already found if you take In is equal to minus 1 by n open intervals, then we found intersection n equal to 1 to infinity is empty. There is no point common to every In by Archimedean principle of real numbers. And if In is a nested sequence of unbounded intervals, then also you can, for that let us take an example like this. You take whether it is closed or not, no problem. You take 0, then 0 infinity, 1 infinity, 2 infinity, like that. If you take this is an unbounded interval, no? That is let us say, like, let's start with 1 also. So let us take in is equal to n infinity, n infinity. In is n infinity, where n in n. N in n. Let us take. So what is that sequence? It can be closed, left closed, no problem. You take open interval. 1 infinity is the first, 1 infinity is the first I1, and the next interval is 2 infinity, the third interval is 3 infinity, like that it goes. Clearly it is nested because 1 infinity contains, 2 infinity contains, 3 infinity, like that it goes, etc. So it is a nested sequence of unbounded intervals. Unbounded, if you take the left closed, then also it is unbounded intervals. You can see that there is no common point which belongs to every, because when n becomes larger and larger, it moves towards infinity. And infinity is not a real number. So it is very clear that intersection in n is equal to 1 to infinity is empty in this case. So the nested interval property is satisfied only if we have a nested sequence of closed and bounded intervals. If it is open, need not be true. Similarly, if it is unbounded, then also the result may not be true. That's how the nested intervals property theorem. In the next session, we will prove a consequence of nested intervals property theorem. So that we will discuss in the next class. Thank you.